Hello, ladies and gentlemen. Welcome to the EU Green Week partner event titled Skills Guiding the Green Transition of the Plating Industry. My name is Maria Gianti. I'm a project manager at Excelsis, an engineer-based consultancy company located in Athens, Greece. It is my pleasure to stand here before you today as the dissemination manager of the FreeMe project, and I'm thrilled to welcome every one of you in this event. This is a collaborative event between the FreeMe and the Mozart projects that aims to explore the crucial skills that will shape the future of the plating industry. Additionally, this is a great opportunity to have our first cluster activity presenting all 4 projects that have been funded by the European Commission under the topic of safe and sustainable by design metallic coatings and engineered surfaces. So we have the FreeMe, Mozart, Nicefet, and VAO project. I would like to express my deepest gratitude to all our presenters for sharing their expertise and insights. And I will also wanted to extend a special thank you to our distinguished external stakeholder, Mrs. Herman from Robert Bosch, who will be delivering an insightful presentation at the end of this event. So before we begin, I would like to ask you to keep your microphones muted. And at the end of the session, we will have a Q&A session to discuss any questions. So now it is my great pleasure to introduce to you our first speaker, Alessio Carminati from Gasser, who will be coordinator of the FreeMe project and will be presenting a few details about the project. Alessio, the floor is yours.
Thank you, Maria. So let me share my screen for a second. Here. And so, as Maria said, I'm Alessio Carminati, and I'm part of the FreeMe coordination team here in Italy. So, the FreeMe is an Horizon 2020 project founded by the European Union, and it will take around 48 months to be assessed, and right now we are concluding the first year of the project. As part of the project, we have some different realities, both from universities, research institutes, dissemination agency, and industrial partner like automotive, aerospace, and household companies. So, the objective of the FreeMe project basically are 2. One is, so the FreeMe project involves the nickel plating process of the plastic. And in this kind of process, you typically use 2 different chemicals that the project aims to remove from this kind of industries. So the first one is the chromium-6 etching of the plastic substrate, and the second is the palladium activation of the substrate. Of course, both these chemicals are taken inside the reach right now, and in particular chromium-6, as we all know, is particularly toxic and dangerous for the environment. So the aim of the FreeMe project is to avoid these 2 chemicals, to substitute them with a long-term sustainable process using, of course, safe and sustainable by design approach, and all the other aspects that involve the green development of the project. Right now, the objective is also to develop a substitute of the process that is capable to fit inside the already used technologies or to need just a little bit of modification. And of course, to be effective on the industry, you have to respect the same quality standard that are already used right now in the industries with all the products. So, plating on plastic, it's found almost everywhere in the daytime life. So you can see here some trim, some plastic part inside a car that are covered in metal, and they are made, of course, of plastic. The most used plastic is ABS or ABS polycarbonate, and this kind of materials is widely diffused almost everywhere. So basically, the process involves a first step in which the surface is made capable of sustain the metal plating at the end of the process. So we have an etching with hexavalent chromium that roughens the surface, and then an activation with a noble metal with palladium that will maintain the substrate capable of reach the chemical nickel, the electroless nickel on it. So these are basically the step involved and the type of parameter of a standard process. There are quite a few, also because it's quite a mature process, the one of plating on plastic. But basically, the more toxic step is, of course, the one involving the chromium 6. So chromium 03 and sulfuric acid at high temperature, and this will cause the selective etching of ABS with, let me say, a good property of the surface for most metals. These are the effect of a chromium 6 on the surface of material seen at the microscopes. And after that kind of process, we have a series of steps that involve the neutralization of the chromium, also to be sure not to put it in the environment, because it is an high risk of pollution and permanence in the environment. So the next step are just a preparation with hydrochloric acid, and then we have an activation with colloidal palladium that is quite not economical, but right now is the most used solution for the activation of the surface, and of course also because it's a very good activator of the surface. And then some other steps that involve the final activation and the plating of the plastic. So FreeMe has two types of technical approach to remove chromium and palladium. The first one is using a special resin developed inside the FreeMe environment that use a green process and let's say sustainable chemistry from the beginning of the synthesis of a resin. This kind of resin will be composite and will include some metal particles or a particle of a salt of a metal that will do the same thing as the palladium do, so the activation of the surface. And the etching step in this kind of approach is not is not present just because it's substituted by rotation of resin. On the other hand, we have a different approach that involves the use of other chemicals, but the same type of plant currently used. So is a plant that involves a deep process of a part. So basically, in this kind, the chromium and the palladium are just substituted, but more environmental friendly chemicals like peroxide, some peroxide, of course, not every kind of peroxide, and some other colloidal particles that are able to activate the metal, typically other nickel particles from some precursor. So the output of this kind of process is the inclusion in both cases of metal particles that will catalyze the reaction of electrolyzed nickel on the surface, and then the further plating of the other metals on the surface. And this is the kind of racks and plating equipment that will be used inside the project. Of course, for the project, I'll use also the more modern modelization technique like the in silico approach or some other parametrical modelization, so that the output of the process can be seen before the end of the process, and also there will be a inline protocol that uses some spectroscopy to let's say inspect the part and assess the quality with automotive and aerospace quality. So that's kind of. So this is all from my part. Thank you for the attention, and we'll see each other in the QA session at the end. Thank you.
Thank you very much, Alessio. And now I think we can go to our next presentation about the Mozart project. And I would like to welcome Professor Luca Manganin from Politecnico di Milano to share his presentation.
Good morning, Maria. Yes, just a second. Okay, so you should see it. So shall I start, Maria?
Yes, we can see your screen.
Okay, so but first of all, thank you very much, Maria, for the organization of this great workshop, and also I wish to thank European Union for the funding, which is always useful to arrange these, let's say, meetings and to know the other and to meet the other projects. I will talk about Mozart. I'm the coordinator, so Politecnico is the Politecnico di Milano. Italy is the coordinator of this project. Mozart, as you see, is aimed to the let's say implementation, I would say, of nanocomposite coatings in order to find an alternative to hard chromium. And so even in the title you can see that we can recognize easily some words that are let's say typically not associated with the green approach. So chromium typically is seen as a process, hard chromium plating, as a process not exactly, say, environmentally friendly. In the previous presentation by Alessio, hexavalent chromium was mentioned, and also here, of course, for hard chromium plating, typically hexavalent chromium electrolytes are used. So alternatives are needed. There is also, let's say, this is important for the regulation, for the REACH compliancy of the process, which is becoming really stringent in the next few years. And so the proposal we have here in this project is to implement the electroplating of a metal matrix, and specifically in this project, the metal matrix is nickel. Pure nickel, introducing also a combination with nanoparticles. Of course, the idea of nanocomposite, I will come back on the following slides, is something well known, and actually some of the partners have a lot of experience in this, because we have already worked together in previous projects, developing the electrolytes, developing also the equipment, and showing the scalability, demonstrating actually the scalability of the process and the possibility to use nanocomposites electroplated as a real alternative to hard chromium, at least in specific applications. So, as reported here, the Mozart project proposes sustainable coating solution for replacements of hard chromium in specific applications based on nanocomposite electroplating processes. So again, also here, very simple formulation of the sentence, but really important, because again, we want an alternative to hard chromium, but we are well aware that it is not easy, or at least we will see, to replace completely hard chromium in all the applications. And so we are targeting specific applications in the project. Some components where resistance is fundamental, some automotive parts where we know that the composite can be really a substitute for the hard chromium coating. And so we will try to, based on the, let's say, requirements of the coating, let's say, coming from the hard chromium characterization, of course, we will try to find the alternative as a combination of a nickel matrix with specific particles at the nanoscale that are able to provide exactly the properties that we want. Properties means, in this case, where resistance, friction coefficient, and some other. In the same sentence here, there is another important part, which is sustainable coating solutions. And so, again, we want to provide a process which are which will be REACH compliant, sustainable, and so on. So also nickel, for instance, we know in nickel electroplating processes, there is the discussion, a huge discussion about the use of boric acid. And so, for instance, one of the aim of the project, is to develop an electrolyte for nickel plating without the use of boric acid. I will come back in the following also on this. But the project, 42 months, 16 partners, you see here, about 5 million of funding. As you see from the partners, we have, let's say, a research center for the development of the technology, like Polimi, like Sinano, and others. Fundamental, the use of the characterization tools to, let's say, compare the behavior of the new coatings with the one with the benchmark, let's say, so with our chromium, so Alex tribology. We have a company dedicated to the communication exploitation, like FreeMe, for instance, and then we have like end user and or contributing to the technology like Aymen, Coscunos, Campacas. We have a chemical supplier like Tecnochimica, which is fundamental for the formulation of the electrolytes, and also, let's say, to have a formulation which can be market ready. And then, of course, we have the particles to be developed, or let's say to be tailored in order to be compliant and to be compatible actually with the electrolyte, and so matrix and NBN. And very important, Elsica and Brave Analytics, because there is an important part of the project which is related to the, let me say, generally speaking, at the moment, the modeling and the simulation of the process. I think I forgot the important for, let's say, the experience and the suggestion about the test cases, and that's an innovation, of course, for all the support, the exploitation, IP, and all these aspects. Let's say the idea, as you see here again, is to really exploit and implement the technology of composite plating. And so we start from an experience well consolidated on at the lab scale, actually at the pilot scale. And now, let's say, the idea is to go up to TRL5, maybe a little bit higher, and so to provide what is needed to completely scale up the process. That means formulation of the electrolyte, as I already mentioned, the use of nanoparticles, also in terms of safety, fundamental also this aspect, but the maintenance of the electrolyte for sure, and all the aspects needed in the running of a real plating line. That means also the equipment that we have to introduce in the plating line to keep under control the process. And so here the two important aspects I want to underline, the idea of, let's say, generally, we can say safe and sustainable by design strategy, which is also the aim of the call, as Maria mentioned at the beginning, and specifically for this project, what we are going to implement is an in silico method, so combination of artificial intelligence and simulation methods. This will be very important, let's say, not only for this project, but for the electroplating sector overall, because it's not so common to have this kind of support in electroplating. And of course, here, let me say, things are a little bit more complicated because we have also particles surrounding the electrolyte, we show in a second in one of the next slide. And so these aspects, so the simulation and or in silico method are, let's say, more challenging here because not only we have to simulate the electrochemical process, but also the fact that actually the electrochemical process at the interface is in some way affected by the presence of the particles in the liquid. The other part is, let's say, I mentioned briefly the functionalization of the nanoparticles because, and the advanced electroplating techniques mainly means pulse plating, for instance, and the functionalization of the particles in order to achieve a very good dispersion of the particles, but that is part of the formulation. Important is the online monitoring technologies, because if we want to really upscale and to be market ready for any composite process electroplating, based on electroplating, we need a tool or a system to control very well the presence and the amount and the distribution and the dispersion of the particles into the liquid, because this is really connected to the amount of particles that we are able to co-deposit in the matrix, and so, and also to their distribution in the coatings, and so at the end correlated to the performances of the coating. And so the development of really innovative, let me say, I'm really let's say happy of this approach that we have in the project, and the partners that are working on this really innovative approach to keep under control the amount of particles that can be really scale up to a real plating line, and there will be a demonstrator very soon at Sinano. Maybe some of you are not so familiar with composite, and so you see here a picture. There is the let's say the sort of orange part is the substrate, and the gray part is the composite layer. As you see, the gray is actually the metallic matrix, and all the dots, the black dots that you see there are actually the particles. So the idea of a composite is to mix, to be capable to mix a metallic matrix with the properties of this metallic matrix, in this case specifically nickel, with particles which are able to completely, in some cases, change the behavior of the coating, the performances of the coating, and so the properties of the coatings. For instance, we can imagine to co-deposit very hard particles, ceramic particles, to increase a lot the hardness of the nickel matrix, which is typically not so high in comparison with the hard chromium. But with the use of the particles, especially the nanoscale, the value of the hardness can match the one of the hard chromium. So in terms of wear resistance, for instance, abrasion wear or erosion wear, we can be the coating can be really competitive with the hard chromium. Another possibility is, for instance, to introduce particles which can be classified as solid lubricants. If we want to have not only wear resistance but also a low friction coefficient, we can co-deposit carbon particles, for carbon-based particles, for instance, layered compounds like molybdenum disulfide, tungsten disulfide, and so on. And so again, let's say, using or combining the properties of the dispersed phase, so the particles, with the properties of the matrix. If I go too long, Maria, please stop me. So, why the project, let's say, is challenging? Because, let's say, it seems easy, in this description. Actually, what you see here is a very simple scheme, a sort of a lab scale or beaker scale, if you want, set up for depositing composites. So you have a tank, a liquid, that is the typical case of an electroplating process, even in a real plating line. Two electrodes, the external power supply can be direct current, pass current. Of course, this can be implemented. It's not a big issue. But actually, what you see here is the presence of the particles. In this picture, we can say the green part or the violet something particles represented here. And so here is the major issue in this kind of approach, because if we want, or our aim is to find an alternative to hard chromium, means that the coating should have very high, let's say, values of hardness, for instance, and these values of hardness should be homogeneously collected, let me say, in the overall part of the component. That means that, for instance, the particles which contribute to the increase of hardness should be very uniformly distributed into the layer, into the coating, into the matrix. And so there is two major aspects, the amount of particles and the distribution of the particles. These two aspects are mainly related to on how we are able to maintain the particles distributed and dispersed into the liquid. And so the equipment and the, let's say, handling, let's say, of the tank, imagine in a bigger scale, 100, 200, 500, 1 liter, if you want, is very easy. Imagine that really these tanks can be like 5,000, 10,000 liters. So it's not just a game. And so the equipment, in order to maintain dispersed, is an important part of the project. The capability to analyze and so to see, to verify the dispersion, as I mentioned, the online monitoring, and very important also all the aspects related to the simulation. So the capability to let's say, to foresee how many particles will be co-deposited in specific condition in correlation of the geometry and the size of the component, of the final component. Here the work packages, mainly dedicated to the major aspect I have mentioned. So apart work package 1, management and coordination, of course, as we know, all the coordinators know very well which this say work packages are really important. The first part of the project, of course, we are more or less at the first 1 year of the project was dedicated to the definition of the specification of and the requirements, because this is, again, don't forget that we are within the idea of safe and sustainability by design, and so strategy, and so we have to collect the needs and the possibility that we have to meet these needs and to define the best strategy in terms of safe and sustainability. Okay, so it's not only safety, it's also sustainability of the process at the industrial level. Then, of course, we have one work package dedicated to in silico. As I mentioned, both for the simulation of the electrochemical process and composition, but also for the, let's say, maintenance or control of the process. Work package completely dedicated to the sustainability safe by design, to the use of this approach in plating of composite processes. A work package dedicated to the alternatives coatings, and here, as I said, the major part is the development of electrolytes without the use of boric acid. And I can say that let's say, this objective has been already practically achieved. Then we have work package 6, demonstration activities. There will be some pilot lines with the equipment, with the innovative equipment on board, and also specific applications. So the end user here will play a major role in providing the demo cases and in evaluating the new coating in comparison with the hard chromium. Of course, assessment and market replication. Very important in all the European project, as the dissemination, communication, and exploitation strategy. I think I have said almost everything. Of course, these are my contacts. If you need any information, or if there is any question today, I'm really happy to answer. Thank you.
Thank you. Thank you very much for this presentation of the MOTO project. And now we can move to our next presenter, Dr. Alexandros Zoikis Karathanasis from Creative Nano. Alexandros, you may take the floor now.
Thank you. Just a moment to make this screen. Can you see the screen?
Yes, but I think we are seeing the presenter's mode.
Screen. Okay. I will change it. Is it okay now?
Yes, now it's perfect. Thank you.
So thank you, Maria, for this organization of the workshop. When we first discussed with Maria about the potential presentation in this workshop, we said to try to have a presentation that will be in accordance with the target of the EU Green Week that actually for this year is job skills, and how novel job skills can enhance the sustainability of various industries. So I try to make a presentation that is related to job skills in plating industry. We will start with a short introduction about our company Creative Nano, some aspects about the plating industry, the market and the employment of workers in the plating industry, job skills that we need, and new job skills that we need, and we will conclude with some examples on how this advanced, let's say, job skills can assist the overall electroplating industry to move forward to more sustainable solutions. So Creative Nano is a small medium enterprise that has been founded in 2013 in Athens. We're now currently 12 persons working, 7 of them have PhDs. We provide different type of services, mainly in the nano technology, nano coatings, dispersions, etc. Of course, our main target is to develop new type of coatings utilizing electroplating or electroless plating processes. We have synthetic labs, pilot lines up to 250 liters for demonstration activities and small scale productions. We have 3D printers and then fully equipped laboratory for characterization with SEM, XRD, DLS, FTIR, UVVs, etc. As I said, we can work on electroplating and plating of plastics, synthesis and modification of nanoparticles, enhanced photocatalytic properties, various preparation methods with a great focus on the ultrasonication process and additive manufacturing. Here we have some projects. I included the ongoing projects, except from Pure Nano that has was finalized some months ago, coordinated with by Luca from Politecnico di Milano, that was related to the purification process of plating baths. Nanopad is a project, ongoing project about methods, development of methods for analyzing in situ nanoparticles for composite plating. Sabidoma is a sustainable by design project for development of new type of processes and equipment that will be more sustainable and safe for the workers and the environment. Diagonal is very close to the Sabidoma project that I said before, but it works mainly with 2D nanoparticles like graphene. 3D Plate is a Greek national project about plating on plastics, and the two projects that has been already presented by Alessio and Luca, the FreeMe and the Mozart project. So, plating industry. The global electroplating market value and growth projection we can see here. We are discussing about an industry that is estimated around 24 billion euros. This number consists the plating shops. I will explain also later what I mean, but when we are discussing about the electroplating industry, there is a big differentiation between plating shops that are shops doing subcontracting jobs and in-house electroplating that many companies, mainly companies have when they have vertical production lines, and the data that we can acquire from them is very limited. So we are see that there is an industry sector that is expected to have a medium year-over-year growth overall. Here is distribution between various places, North America, Latin America, Europe, East Asia. You can see that actually Europe is estimated that will have the lowest growth rate for the next year, and we will discuss about this. The market that are covering, based on the metal that is used and the end user that we work for, we can see that number one is gold, not so much because of the mass, but mainly because of the price. And then we have silver, copper, nickel, chromium, steel chromium plating is a part of the cell, zinc and other. And the larger end user is automotive, and then it comes with electrical and electronics, aerospace and defense, jewelry, machinery parts, and other like silver, optics, etc. The main driving forces. We have separated this. We have the main driving forces that concerns the sector of the surface finishing and the plating, and the supply chain sign trends that are followed by the plating industry show us to have new advancements. So the main driving forces is high demand from ASEAN countries, increased demand from diverse industries, and this is a very important issue for what we will discuss in this presentation, that electroplating, plating, etc. Covers a large range of applications. It's not a a process that is focusing on automotive or aerospace only. There are a lot of different applications. That means a lot of different specifications and standards. We have many emerging applications in the automotive industry, especially now with the electric vehicles. Many things are changing, standards are changing, new opportunities are emerging. And finally, a main driving force, especially for Europe, this is not so valid for Asia, is that we have increasing stringent environmental regulations. That means many substances, many chemicals that are currently used by the industry, the European Commission has decided either to ban or to restrict their use. So we have, for example, as Luca said, the hexavalent chromium, boric acid, PFAS, etc. So this is what we have to take into account for the next year. And when it comes to the supply side trends, we have development of new and innovative products and customized solutions for clients. So this goes a lot on the technology of 3D printing additive manufacturing. That is a technology already introduced in the industry, in the manufacturing process. And as the plating industry is a sector that goes together with the manufacturing process, this is a new field that the plating industry will need to cover for the next year. And when discussing about 3D printing objects, then we're also discussing about different substrates, morphologies, etc. Increasing investments in wastewater recycling, there are an ongoing big effort in order to reutilize the water. And we know very well that the plating industry is a main water consumer for the bath and the rinsing processes. And then there are collaboration with end user at a regional presence. This means that although in the past decades it was easy, for example, European companies, European manufacturers to transfer their products to Asia, Latin America, etc., for lower prices for the process, now transportation cost has risen, so there is a shift back to European plating shops to do the job. So, and we have here some impact analysis of the main key success factor for the plating industry. So, important factors that have a very big impact on the process on the industry is equipment and service coverage, availability of wide range of services for different applications. This comes with what I said before, that is electroplating and plating industry in general is a very diverse technology applied to many different applications and many different industries. Equipment, and mainly automation and robotics, seems to be a very important part of this game. Proximity to end users, better communication and understanding of specifications, increasing emphasis to the aesthetics and durability of decorative products, flexibility on adoption of new technologies, and then slightly less important is service track record, safety record, and proven expertise in service area, and then focusing on large-scale applications. We have put this as the less important factor because the diversity of the industry, and especially now the customization, mass customization of products due to the 3D printing manufacturing process will change this scale of economy that we had in the past. Now, when we come to the job skills in plating industry, I will link this with the impact analysis of the key success factor, because the more important part for a successful company is its personnel. And nowadays we are discussing about high-skilled personnel in the plating industry. Of course, high-skilled personnel with deep knowledge of the science, etc., means higher labor cost. However, we should see this always as an investment for a plating shop, because despite the fact that we will have to pay higher salaries, the overall cost of the production will be go down, mainly because of the four aspects that we are discussing here: adoption of new technologies, new ideas that could lead to optimization of processes, in-depth analysis of customer needs and specification, and of course, the application of new digital solutions. So, as I said before, we have plating shops and in-house plating facilities. Based on some recent data of 2019, it is estimated that around 250 to 300,000 persons are employed in the plating shops. That means to the subcontracting facilities. And it is estimated that a similar number is occupied on in-house facilities of large enterprises. When you go to the plating shops, the average number of employees is between 11 and 12 per company. So that means what we call family businesses mainly. And we should also say that the vast majority of these plating shops, that means more than 60%, employ 1 to 10 persons, mainly usually 5 to 6. So we can see that there is a big differentiation here. We have a very big number of very small companies and a small number of larger companies that occupy more persons. Finally, the level of automation is proportional to the size of the company. That means the higher and more personnel the company have, the more application, the higher level of automation has been applied to such companies. Here we have the basic structure of a plating shop. So we have operators of plating lines, metal workers, and machining. This is not always the case because some plating shops, they are just doing only the plating process without the preparation of the samples, of the metal articles. We have engineers, chemists and chemical engineers, and of course, sales managers, but we will not discuss about them today. Additional positions are quality control and research, that this can be covered, of course, from the engineers and chemists, chemical engineers. But again, this is a part that is not always seen in many plating shops. So when it comes to operators of plating lines and metal workers, we have, for the production and processes, we have people that should have good knowledge of raw materials and chemicals, basic math calculation, knowledge of basic quality control systems, equipment operation and monitoring, and basic knowledge for maintenance of this equipment. Always, we should know that they should be trained to have excellent knowledge of safety procedure, as we are discussing about a high-risk industry because of the heavy metals and the significant of environmental damage that can be done, as well as on the health of the workers. So health and safety measurements should be always one of the main training courses for people working on the electroplating industry. Soft skill, it's critical thinking, listening, speaking. Listening means that people should understand very well what their colleagues are saying, and also to say potential problems that they have in production, team working, and time management. When it comes to the higher level of personnel that we are discussing about engineers, chemists, and chemicals engineers, for the best part, production and processing, the hard skills, they should have excellent knowledge of raw materials and chemistry of baths, excellent handling of equipment, operations and monitoring, understanding of basic IT. This is something that is very important nowadays, that we have the digital solutions, deep knowledge of quality control, including advanced characterization techniques, understanding and translating end user specifications, excellent knowledge of applying and monitoring safety procedures, deep knowledge of standard and legislation. And for the soft skill, organization, leadership, critical thinking, team working, and time management. Here we have put some what we call advanced skills that someone cannot find in every plating shops, but given the fact that we are discussing for the transition to a greener sector, as Luca, for example, said before, the replacement of hydromium, we have put some skills that we believe that nowadays plating shops should have on the workforce. So we are discussing a bit about deep knowledge of electrochemistry, knowledge of nanotechnology, surface chemistry, simulation and modeling, data management, artificial intelligence, and machine learning. Here, we need to say that traditionally there was a confusion about the plating process, if it is a technology, a science, or if it is an art. Even today, we can find plating shops that are considering that based on the experience and based on what the olders have done, they can continue working on the same processes with the same way, having the same always result. So we can say that unfortunately the plating industry is a hard to innovate sector, meaning that new advancements, innovation, etc., are difficult to be adopted by the industry. There are two reasons mainly for this thing. The first reason is what I said before, that plating shop are small family business that the workers and the owners of the business knows very well what they are doing, because they are doing this for many, many years, and it is successful, okay? Successful only towards the result of the coating, not the overall process, its sustainability, and if it is environmental friendly. And the second main reason is because many plating shops, they have to follow standards given by the end users. So they cannot easily change processes unless they have the okay and the approval from their end user. And that's why we believe that large scale projects like the one that were presented before, FreeMe, Mozart, and other European projects, we will also have two projects later on, are very, very important, because with such project, we bring in contact end users with the providers of the technology. So the end users can test, demonstrate new technologies, and through this way, we can change their specification and standards. So, concluding, we have put here a series of examples of how these advanced skills can assist plating shops shifting to a more greener technology, environmental friendly, sustainable, and of course, of less cost. So, today there are a lot of efforts to replace existing baths. A very known bath is the VATS, nickel VATS bath, that contains boric acid, that now, based on the fact that boric acid has been characterized as a substance of very high concern and has been listed, we should make some transformations of the bath. So the first step to do this is to work on the electrochemistry of the bath. So here we can see some examples that has been run in Creative Nano, utilizing advanced electrochemical stations that can do cyclic voltammetry, scan dependent cyclic voltammetry, chronocoulometry, etc., in order to see and extract exams about the use of various acids beside the boric acid, and to have a first indication about how these new formulated baths can behave based on the electrochemical profile. For example, we can see from cyclic voltammetry about the potential of the reduction of nickel, if it is easy to be done or not. We can see from scan dependent CV the estimation of the diffusion in the bath, and of course chronocoulometry that we can extract some things about the mechanism of the electron deposition, if it is a mass transfer or charge transfer, etc. As Lucas said, a very big effort is also done in the nanocomposite coatings. We have here a combination, because we show here a composite coating with a new type of bath other than the VAT type. So we have used, instead of boric acid, oxalic acid, and nanoparticles of silicon carbide in a size of 200 nanometers, using a standard pH of 4. And with direct current resin, we can see that we can have a good distribution of the silicon carbide. We have reached 4.5 weight percent. Of course, utilizing more advanced methods like pulse current plating, this can increase. And as you can see, we make comparisons of the efficiency and of the hardness of different type of coatings with different type of applications. Another example is the redesign of plating baths, especially when it comes to the composite plating, where we do have particles inside the bath solution. This is a very big change for the bath. So there is a very big need to keep nanoparticles always in suspension. The level of the dispersion that we will achieve in the plating bath is the level of the dispersion that we will have for these nanoparticles in the final coating. So excellent dispersion in the electrolyte means excellent coatings. So here, this is a combination of the Sabidoma and Mozart project. You can see how we can shift from a single tank bath to two tanks that are connected, in which we can apply ultrasonication so as to increase the dispersibility of the particles inside the solution and to achieve better coatings. It is characteristic that with the traditional one tank bath, we can achieve under the same always condition of plating coatings that will have 0.2 silicon carbide with a very bad distribution, two coatings that can reach 3% of silicon carbide with an excellent distribution. And of course, this is translated, as you can see, to a better hardness, a vast increase of the hardness from 500 to 800. Additionally, we can have reduction of the wastes in the racing tanks in a level of 85% for silicon and 65% of nickel, what we call the drag out phenomenon. Green plating of plastics is the FreeMe project, and what you will see here is a combination of the FreeMe project and the 3D plate project that we have run in Creative Nano. So without the use of chromic acid, without the use of palladium, we can modify the plastic surfaces or the resin surfaces. This is an example from a 3D printed resin object. And we can see here with FTIR analysis how we can transform the as-printed surface to a surface that can have some active links in order to attach the precursors for the electrolysis plating process. We can see here with some images and EDS analysis the level of the adhesion. Here we have the substrate, the coating, and the boxing resin. You can see that we can have an excellent anchoring of the coating in the substrate using such technologies and different type of coatings. Here you can see final object. We have some rings that are started with electrolysis nickel, a nickel type of bath, copper, and final top coating gold, and of course copper plated or zinc plated. Finally, this is an extraction from the Mozart project. We can have the development and the utilization of IT tools in order to develop predictive modeling or decision support tools that can assist the overall industry, plating industry, to shift to more green technologies through utilization of data generated by experiments or generated, as Luca explained before, by in silico technologies. So we have the user specifications as starting point. We have modeling and simulation, we have experiments, we have loops, so as to deliver a final, quick final presentation of how a new bath should be set up in order to have a good final result of the coding. So I would like to present the team that has worked for this presentation: Mrs. Eleni Poupaki, Dr. Fotis Kamatsos, and Dr. Alexis Vouropoulos, and of course to say thank to the EC for providing the funding for this research work. Thank you very much. I don't know if you have any questions.
Thank you, Alexandros. I will kindly ask if you have any questions to write them in the chat box. And now we can move to our next presenter, Mario Santiago Herrera from ICC RAM University of Burgos. Mario, you may take the floor.
Yeah, I'm sharing the presentation now. You can see it, or is not?
Yes, we can see.
Okay, perfect. And in full screen, right?
Yes, perfect.
Okay, perfect. Okay, so sorry, I'm going to speak about the safe and sustainable framework on these metallic coatings and generic surfaces that the previous speakers spoke about before. Just to start, a brief introduction about our institution. I am working for ICRAM, which is a research center associated to the University of Burgos, which is located in the north of Spain. We are currently participating in about 20 European projects that you can see down below the logos. We are about a team of 25 people. We have different research lines. One is devoted to materials design and synthesis. We have another one for environment, toxicology, and biotechnology. There's another for electrochemical processes, and another one for sustainability and circular economy related aspects. Yes, regarding the safe and sustainable by design, for metallic coatings and generic surfaces, the idea is to produce these products without the use of toxic substances and heavy rare elements, as for instance Alexio explained in the first presentation, and also engage the performance of these products. And it's currently a really important area of research and development, with more and more research and studies on these topics. In the last years, or in the last decades, let's say, the European Commission has released different directives and strategies, like the European Green Deal or the Circular Economy Action Plan, trying to reduce the negative impacts on human health and environment. And finally, at the end of last year, in December, there is this Commission recommendation for establish a European assessment framework for safe and sustainable by design chemicals and material. So under this framework, we are going to develop our safe and sustainable by design strategies. This framework is divided in two stages. The first one is the redesign, and the second one is the safe and sustainability assessment. It was like an iterative framework. That means that you first start with your first design of your process or chemical or material, and you do the different assessments, and then with those results you can redesign in basic or some principles that I'm gonna show now, and then you can assess again and see the difference and how you are improving your products. So it works like this. This is a scheme to better understand. We have first the design principles with different action and indicators, and it works in an iterative way, and also helps to increase the innovation of the process. And then we move to the safe and sustainability assessment, which comprise 5 different steps that I will also explain later. So regarding the first stage, the design or redesign principles, those are the principles established by the Commission. They are mainly about the efficiency of the material, so to use fewer raw materials and generate less waste. Also, try to use chemicals or materials that are not hazard. Also, it's important to minimize the energy use and change to renewable sources. Also, in between the process, try to avoid some of the emissions that normally you can have. And also, it's inside this thinking of the life cycle and trying to also design for the end of life of this product, so they can also easily get into the change again. So for the second stage, which is the safety and sustainability assessment, it works in a hierarchical approach. So the most important part is the safe of the toxicology of the chemical and the material. So if it's safe, it can pass to the next step, which is to assess if it's environmental sustainable, and then we have the last step, which is to assess if it's socioeconomically sustainable as well. Okay, so just to show it all together. For the safety, we have the 3 steps. The first one is the intrinsic hazard properties of the chemical or material. Second, we have the occupational hazards during the production and processing phase. And the third step is related to the application or use phase of this material. The step 4 is the environmental part, and here we use life cycle assessment methodologies. And the last step is the social and economic assessment. And there are different aspects that you can evaluate here, and with different methodologies that are still under in a lower mature state, but they are developing right now. So here you can see maybe more easily. The first step is the hazardous properties of the chemical or material. Then you have to assess the production processing. The third one is the exposure or the final application of that product. And at the end, we have the environmental impacts in the different how they can affect to the air, for instance, of the soil, water, etc. So in the safety part, we assess all the value chain, and for the hazard, for instance, we assess the human health hazards with different indicators and different techniques that I'm not gonna go in deep detail in this. Also, we assess the environmental hazards, so how these chemicals or substance release can affect to the environment, and also physicochemical assessments. And then we assess the exposure pathways for humans and also for the environment. And once this is done, we can pass to the environmental impact aspects. And here we use all the inputs and outputs that are coming in the different parts of the value chain of the production process, and the different impacts are related with the sustainable and development goals. And now we are gonna see all the steps one by one. First, we have the step 1, the hazard assessment. There are different criteria that this chemical has to pass in order to continue the assessment. So as I said before, the step 1 is the most important. If the substance is among the most harmful substances, it's a cutoff criteria. So you cannot just stop there, and that's a no pass for this substance. And then you have other criteria like if it's a substance of concern, or if it's have another hazard properties. And then if you pass those levels, you can continue with the assessment to the second step. In the second step, is related with the occupational health and safety issues. And here we have different criteria, and depending of the risk, we can give different scores to the the substance under assessment. And then we pass to the final step related to safety. And here we assess the exposure of the material, and then we also make the different score depending on the criteria, and if it's above the safe level or if it's below, and then we give different points to that substance. And if we pass these 3 steps, then we can continue to the sustainability part. And here we have the step 4, which is the environmental sustainability assessment. It's also divided in different criteria. One is for toxicity, and the second one is for climate change, then also for general pollution, like particles, etc. And then also we have criteria for use of resources. And we assess these different criteria by the life cycle assessment methodology, and depending on the improvement that we have with this new design, we give different score, and then we can see if we are passing to the next step of the assessment. And the final step will be the socioeconomic assessment, which is now under an exploratory phase. So here we can use life cycle cost analysis. We can also use cost benefit analysis, and also social life cycle assessment, doing questionnaires for society or local community or workers, and see how is related to the substance under assessment. And once this is done, we can have a document with all the steps. First, we have the design, and we see if we are passing in all of these redesign principles that I saw at the beginning of the presentation. Then we have a table with all the detailed assessment of the different criteria, and then we can give a final score. And then with this score, we can compare one substance or another substance, one chemical or another chemical, or 2 different processes, or our process with a new redesign stage, etc. We can compare with these numbers, and then we see if we are going forward in a sustainable and safety approach or not. And so this is the framework that we are gonna apply, for instance, for the FreeMe project. We will focus in 3 different strategies. The first one will be the safe by design, to reduce the physicochemical and ecotoxicological properties of the materials, and also we will implement some strategies for the process. Then we will move forward to the sustainability by design strategies to increase the sustainability performance of the process related to the project. And finally, we also include some recyclability and reparability strategies. If you want to go deeper on this framework, you have the Commission recommendation that I said at the beginning, that it was released in December last year, and also there are 2 technical reports for the Joint Research Center about the safe and sustainability by design for chemicals and materials, which are also very interesting. And that was all for my part. If you have any comment on this or any question, you have here my contact, and you can write me an email, and I'm happy to answer. Thank you.
Thank you very much, Mario, for this presentation. And now I would like to give the floor to my colleague, Dr. Kostas Spyrgakis from Excelsis. Costa, you may take the floor.
Hello, can you hear me?
Yes.
Also, can you see my screen, right?
Yes, everything is perfect.
Okay, great. Okay, so hello everyone, also from my side, and thank you very much, Maria, for organizing this great workshop. So my name is Kostas Spyrgakis, and I'm a project manager in Excelsis company, an engineering consulting company located in Athens, Greece. And also Excelsis is a partner of the FreeMe project, where besides the dissemination and training activities there, Excelsis is also responsible for the development of the decision support tool, which will be used in order to assist decision making concerning design and optimization of the FreeMe technologies. So the discussion today is going to be focused on the overview, actually, of decision support tools, their capabilities, and overall the presentation is going to be structured over 5 sections, where they include the introduction, the presentation of the decision support tool concept and industry-driven cases. We'll have a discussion about the problem description, a discussion about the modeling strategies, and finally, we're going to close with a set of illustrative examples. So it is appropriate to begin with a general description of what decision support tools are, which can be easily understood as actually any kind of computer-based application that can be used in order to assist decision making of any end user. Either this end user could be an engineer or a CEO or any citizen to assist the citizen in his or her everyday life. So why are decision support tools used? The answer is straightforward: in order to analyze a set of data and information, and in order to return a set of best or even most appropriate solutions to cover the needs of the end user. And how do they do it? They combine actually user-defined data and knowledge, which can be originated by any kind of knowledge domain, and they can be used, and they are using models, algorithms, techniques, and they're creating new data and knowledge related to the requested problem by the end user. So we could better understand even these terms through two very well-known decision support tools that almost everyone here might have used. One of them is the Google, and the second one is the navigation systems. So what do? They receive an input from the user, like a keyword to search or a destination, respectively, to achieve. And what they are providing, in the case of Google, they are providing most relative pages, and in the case of the navigator, the GPS provides the best routes to reach a specified destination. So we can easily understand that decision support tools can provide propositions of solutions for a wide range of everyday and also industry-driven problems by providing, by processing data and by proposing predictions for near or even for long-term outcomes. They also are used for planning and scheduling of almost any kind of process or procedures. In most cases, they definitely work as optimization models in order to return best solutions. They are also able to consider for user-defined specifications and limitations set by the end user concerning products or processes. And of course, they can be tuned in order to propose mitigation measures for and face potential risks. So all above are commonly driven by one or more objectives, and this could be, for instance, to minimization of investment or the operating cost of a process, or even the time or the effort that we want to minimize, or on the other hand, of course, to maximize profits from products or the provided services. So which used to be the conventional decision-making approach before latest advances in decision support tools. So actually the user, for instance, an engineer, had to follow several trial and error cycles, which may take days or weeks or months. And most times he had to make intermediate decisions, mainly based on experience or very simplified methods. And of course, the engineer has to follow such cycles until reaching a better goal for decision-making purposes. And actually, these final solutions may be subjected to non-optimality. They may be sometimes subjected in, they may be are biased by the opinion and the selections of the engineer, while still it's still possible that some of such solutions might be harmful or may be even infer bad impacts in the future. So instead, a decision support tool can examine the numerous parameters and variables of the problem, and actually it can provide, even in a few seconds, a set of best solutions to better guide the user, considering so much present as well as future conditions, and ensure better solutions than the conventional approaches. So in this scope, there are different types of decision support tools fitting to the specific demands actually of its problem, and are available in the arsenal of decision support tool developer. So one of the most common type of decision support tools are model-driven decision support tools dealing with simulation or optimization models, and they are returning actually trade-offs and what-if scenarios. Other cases are the user interface decision tools, which offer working interfaces for directly insertion of data and visual checking out of the outcomes. We have communication decision support tools, which offer a common language for collaboration of multidisciplinary teams, and they can be definitely used for collaborative decision making. We have data-driven decision tools, which process dynamically the inserted data, and they are serving actually outcomes based on the existing knowledge that we have so far, like, for instance, like a catalog system, and they perfectly fit for real-time optimization and integration with external sources when, for instance, we can use in industry Internet of Things. Next, we have knowledge-driven tools, which actually are equipped with problem-solving expertise, and they can consider constraints related to facts, rules, and procedures. And finally, one of most latest advances, we have the database management systems, which also significantly raise along with the growing and the complex, let's say, internet domains and the online applications, and they are capable in order to manage unstructured information that they hold different formats, sources, and disciplines. And one of such cases could be also the case of Google that we said before. So drawing on above discussion, we can easily exclude the typical structure about the operation of decision support tools, and we can identify some potentials from their use in industry-driven cases. So a decision support tool is composed of models and algorithms. They also include data, criteria, objectives, and other any case-by-case component that they are needed in order to process, as you see on the left, any kind of user-defined inputs and case-specific conditions, while finally, as you see on the right, they are returning a set of most appropriate or even optimal, in some cases, solutions, conditions, and guidance in order to assist the decision maker, while they also provide options if appropriately designed. They also provide options and capabilities for visual presentation of the results. So now, bringing the context of the decision tools in industrial dimensions, let's say, there is a wide range of potential applications where decision tools are used, differentiated, and actually adapted. So scheduling industrial tasks consists one of the most common problem where they have been used, which is actually usually we're using models based on surrogate. We're using surrogate models or simulation models and optimization models. Other decision support tools, they are further focused on individual unit operations. They commonly consider thermodynamics. They're considering yields and experimental data, and they are used in order to tune or optimize the design and operating condition of a process, like, for instance, the design of a complex reaction separation system. Moreover, recently, in context of also Industry 4 and Industry 5 applications, such decision support tools can operate and interact real-time with other processes, with other units, and also with robotics. So now, when the case is to screen alternative options, for instance, to re-engineer or advance an existing or a new plant, here, decision support tools come in order to address the new industrial limits with respect to the new value chains that are connected with existing and new components that we want to further integrate and advance existing plants. And last but not least, decision support tools can be also used by combining engineering or management and even economical terms in order to examine trade-offs and to identify regions of optimal operations in order to minimize cost and ensure safe and sustainable design and operations. Next, decision support tools can also actually consider various constraints and identify limitations in the optimization space. And actually, we have to admit that the more complex the problem is, the more constraints and equations should be considered in the problem. And thus, we have an increase in the size and the complexity of solving procedure of such problems. So one actually could build and solve smaller problems, of course, on paper, or they can also use Excel spreadsheets. However, when the problem comes with hundreds or even thousands of variables and equations, then the developer actually need to build the decision support tool in appropriate environments like GAMS or MATLAB environments in order to deal with such big and very, very complex cases. Other options, when interoperability, for instance, or common languages are required, for instance, in software applications, then other programming languages like C++ or Python or others could be used in order to appropriately handle the models and connect and the different models, the modules and databases together in a whole and single application. Another benefit is the use of multiple objectives in order to examine trade-offs of different goals, like the safe and sustainable by design problem. And that could be, for instance, the trade-off between environmental and profitability goals. So accordingly, the preview of objectives over, for instance, a Pareto graph can be used in order to identify best regions of operations, or even probably the developer can appropriately weight the different objectives by promoting a global objective for the whole application. Next, we will focus on the problem description, as it is actually one of the most important steps in developing decision support tool. So it is fundamental to understand the nature of the problem and identify the best route to describe and depict the problem through a generic representation. So one typical approach uses decision tree format, which is also commonly called as a superstructure in some cases in engineering, where different design and decision options actually are packed, let's say, by using the boxes or nodes and arcs, which are connecting all the different components of the decision tree. So using this, one could prepare actually input and output balances across the components of the superstructure by using so much continuous as well as binary variables, which can be used for the activation and deactivation of different kind of options. And furthermore, next step, actually models are further included in order to describe the behavior of the different subsystems of the problem. And this can be, for instance, detailed plant simulation models, even for the whole plant, for all the technologies of a plant by using engineering environments like Aspen technologies, or models even for very specific processes of a plant like a distillation or maybe a plating bath. And of course, the whole superstructure could be also duplicated for each time period of the problem in order to actually provide the modeling of a scheduling problem and address scheduling time variant problems. So based on the problem representation, the modeling background runs in order to identify best leaves of the decision tree. And by this means, trying to optimize, to maximize or minimize the value of the user-defined objective function. A step further, post-analysis of the decision support tool outcomes may also require other decision tools that can be also used in order to optimize the integrability of the alternative of the alternative options provided by the previous decision support tool. And by this means, we can further improve savings or further improve optimality of the proposed solution. So having now the superstructures, having the decision tree, the next question applies for the types of the different models which can be used and integrated in order to model the different outputs for each component of the superstructure. So first, one could use, for instance, state-of-the-art models when modeling applies for well-known and typical industrial operations, for instance, a chemical reactor or an exarchon column. So these are typically based on mass balances and thermodynamics, and they are trying to simulate the outputs of a process unit with respect to the alternative process inputs and the design conditions used for this specific unit. Secondly, when the unit or the process are not well defined in literature, and where the developer addresses complex systems with non-homogeneous responses across the problem domain, then regression and surrogate models can be used and built in order to relate the different inputs and outputs of the processes that we are going to address. And moreover, one could also find another source of data that could be originated from computational simulations, where very detailed and very demanding models like computational fluid dynamics, which are not beneficial to get included in the decision support tool. This type of models could be actually used alternatively in order to produce data and use this data to make more models. So by using this data, we can produce and prepare surrogate models of over the different operating regions. And by this means, we can accelerate modeling and the solution part, and we can make quick and robust calculations across the whole problem domain. And based on all above components used in decision support tools, we could also present, let's say, the nature of a decision support tool through a quite simplified illustrative example. So let's say that one case could be the optimization of a multiple stage production line. Here we have the individual process models for each processing stage, where each of them is calculating the output compositions or the specifications of the product. And specifically, we can use, for instance, state-of-the-art models at the first stage, at the etching, for instance, bath, which can be used in order to model a typical reaction system. While, for instance, the second stage, where we have more complex systems, we could, for instance, use in silico-based results in order to model the stage by providing a surrogate model or other regression models that they are simulating the different operating regions of the states. And finally, we can also prepare additional regression models that could be used in order to simulate the response of the final stage. And this can be used also actually to calculate the value of selected specifications, like, for instance, the adhesion of a metal coating. So for each stage, we have also considered additional process and user-defined specifications constraints, as you see in the bottom of the slides, like the capacity of the bath, or this could be the production yields. And actually, these specifications and limitations actually are represented as inequality, and all this set the additional constraints in the optimization model which will be used for the optimization of the operating conditions of the whole process. So now this is the whole set, let's say, of equations that need to be solved together in order to optimize and achieve the objectives that we need by using specific solvers, which are accordingly selected based on the nature of the involved equations. So let's say, for instance, the procedure of processing this kind of data and models for the decision-making purposes through a visual example. Let's say that we have here the adhesion lines of metal coating, and let's say that this is the only constraint set by the end user. So based on experimental data, we prepared regression models that can be produced in order to estimate the adhesion value over the different concentrations and operating times of the previous production and plating etching step. And this kind of regression, yes. And these lines are presented through the three curves, and each of line represents the operation for the three different concentrations over time. So next, the user-defined adhesion specification actually sets the limits over which the process is allowed to operate. And as a result, we identify the time ranges in order to operate over the different concentrations. And actually, we can also graphically identify that the highest adhesion is achieved by operating at concentration C2 and actually at about 8 seconds of processing. But is this the solution? Is the solution the best? Probably not. And why? The reason is because the objective is not to maximize the adhesion. This specification is actually also already ensured by catching the specification in the blue and the red region. So the operator can decide on any concentration and time in the blue and the red regions in order to maximize the objective, which could be, for instance, the cost of the process. So the cost objectives as a function of concentration and time will be also included into the model, and will be also calculated for the different operating regions. And by this means, we can also include more objectives to address trade-offs for different objectives related, for instance, for environmental or safety objectives and purposes and analysis. So in addition, the decision support tool developer could offer an additional feature of the DST by also weighting the different objectives and provide also one single and global objective which could be considered for the optimization of the whole problem. Of course, considering any kind of compromises among the different objectives that they are used in the overall objective. And now, before closing, it's quite important also to set the decision support tool context in contexts of emerging machine learning dimensions. So such technologies can positively be affected by the implementation of decision support tools, for instance, in real-time monitoring systems by filtering, mining on, and analyzing big data. Another consideration could be the integration of machine learning techniques, for instance, to reformulate and calibrate the models of decision tools with respect to different environments of the different input data. And finally, another approach could be to set up, for instance, a post-decision support tool model in order to analyze the outputs and let the decision support tool learn from its outputs. It's like self-training, the decision support tool, and actually it's like mimicking human intelligence. And to sum up, so today we discussed about the capabilities of the decision support tools and the different types of decision tools that can be used for the different cases and problems. They can be also used for predicting outcomes or scheduling and optimizing processes in order to mitigate different kinds of risks and costs. And we also discussed about the context of applying decision tools, so much industrial applications, as well as in general in everyday life. And all these cases can, in all these decision support tools, we can use, for instance, state-of-the-art or regression or in silico models, which can be used in order to formulate the modeling framework of the decision tool and build the problem superstructure, which are going to be used for decision making. And finally, of course, the developers should always appropriately examine and decide about which are the available data and which are the models that want to be used in order to ensure and maximize reliability, consistency, and actually precision of the decision support tool outputs. And with this, I would like also to thank you for your attention. And of course, I'm available for now or later for any kind of questions. Thank you.
Thank you very much, Kostas, for this presentation. Now I would like to move on to our next speaker and save all the questions for the end and the Q&A session. So I would like to welcome Dr. Aliona Nikolenko from CDTech, member of the coordination team of the NIC Effect project, our clustered project within the same topic, also funded by the European Commission. Aliona, you may take the floor.
Thank you, Maria, and hello, everyone. Thank you for the introduction. So let me share my screen. Okay, now, can you confirm, please, that you see the presentation?
Yes, it's perfect. Thank you.
Okay, perfect. Yes, so in this presentation today, I will be introducing the NIC Effect project on behalf of the coordination team. Elena is also here today with me. So we are coordinating this project from CDTech Surface Engineering, so we are connected from Spain. And yes, as Maria mentioned, NIC Effect is one of the 4 projects that received funding under the same call, under Horizon Resilience call, together with the FreeMe, Mozart, and Nouveau project. So NIC Effect stands for nickel-based ferromagnetic coatings with enhanced efficiency to replace platinum in energy and digital storage applications. And well, just to give you a general picture of the project. So the motivation of the NIC Effect comes from the need to find platinum substitute materials for energy applications and digital technologies. Specifically, we are focused on the 3 use cases, and these are proton exchange membrane water electrolyzers, fuel cells, and also magnetoresistive random access memories. NIC Effect gathers a consortium of 12 partners from 7 European countries, as you can see here on the map. The partners have very diverse expertise. So we have 5 small and medium-sized enterprises on board. This is Advent, Iris, Elsica, Magenics, and also F6S. We have 2 universities, Autonomous University of Barcelona and Free University of Brussels, 2 research and technological development centers such as SEA and CDTech. We have 2 large enterprises. These are ANSYS and Singulus. And we also have on board UNE, which is a standardization and normalization organization from Spain. So as I mentioned before, the project is coordinated from CDTech Surface Engineering. This is a technological center that is located at the north of Spain. And in terms of duration, the project has the total duration of 48 months, and it's been already 1 year since the beginning of the project. This is our website that you can visit at any time if you want to find more information about the partners and also about some other activities that are related to the project. And these are our contacts if you want to make a personal connection. So, okay, I go back to motivation. So it is well known that platinum group metals are highly demanded due to their unique physical properties that include the durability, chemical resistance, and of course the catalytic properties, among others. So in NIC Effect, we have identified 3 different strategic sectors that heavily rely on the use of platinum, and these are renewable energy, electric mobility, and digital technologies. So if we want to be more specific, nowadays, platinum and platinum group metals are state-of-the-art materials for water electrolysis and fuel cells. And for example, in the later case, the total cost of the cathode, of the catalyst material that contains platinum or the other PGMs can make up to 50% of the total fuel cell stack cost. If we talk about the digital technologies, this is again another ever-growing sector that relies on the use of platinum. So in this case, platinum is introduced in the magnetic materials in order to provide them with some specific magnetic characteristics. So having said this, it is important to mention that European Commission classifies platinum group materials as critical raw materials, meaning that they are of high importance for the European economy, but also have a high supply risk. And this is captured in numerous reports from the European Commission, different articles, like for example this one, that bring to our attention that nowadays it is crucial for the European economy to develop methods for the PGMs recovery and also find alternative materials to these PGMs. Indeed, alternative materials to platinum group metals can help to avoid the problem of the price and availability, and that is why many works are focused specifically on development of the non-precious metals. In fact, it has been shown that nickel is one of the most promising candidates to replace PGMs in different applications. It is an earth-abundant element with ferromagnetic character that has some interesting properties and is actually widely utilized in different industries. But of course, nickel doesn't have the same chemistry as PGMs, especially in terms of durability and catalytic properties. So it is always important to find a kind of balance between the price and sustainability, but also the efficiency of the alternative material. And from here, basically stems the main objective of the NIC Effect project, that is to develop novel ferromagnetic nickel-based coatings to replace scarce and costly platinum and ensure high efficiency in key applications that I mentioned before. And once again, these are water electrolyzers, fuel cells, and magnetoelectronic devices. So in NIC Effect, we will enhance the material properties by fabricating them with tunable microstructure and various porosity levels. So we also aim at the developing and bringing to the market some new solutions and tools for the materials and process modeling, and as well as for the decision making that can provide some methodologies to follow safe and sustainable by design criteria. In terms of expected result, we are quite ambitious, so we expect to prepare at least 3 novel nickel-based coatings with at least 85% PGM reduction, and without compromising the efficiency, so that we try to reach the same efficiency levels in these materials for each of the use cases, as compared to the currently available platinum alternatives. So these materials, these solutions will be deposited on demonstrators and validated at industrially relevant scale, again, for each of the 3 use cases, thus reaching TRL 5. The deposition process of these materials will be assisted by the development of some realistic models, and again, here reaching a TRL 5. In terms of the material recovery, we target at least 90% of the nickel-based catalyst recovered and reused. And at the end of the project, we also plan to come up with at least 4 commercially exploitable results and some standardization procedures. So, okay, now it's time to present you the main concept of the project. So at the first step, we have identified several nickel-based alloy compositions that could be interesting and promising for the application of each of these specific use cases. And then we adopted several specific tools that will help us to reach these goals, the project goals. So one of them is the adopted deposition techniques. So here we will explore different methods and combination of different methods that will allow us to tune the microstructure porosity of the deposits. So this process will be assisted by the advanced modeling. On one hand, the materials modeling, and on the other hand, the process modeling that I will be talking about this in a minute. And we also have at our disposal support to decision making that incorporates the SSVD approach. So all these tools together will help us to prepare some highly efficient ferromagnetic PGM-free materials that later will be incorporated either as MEAS coating, if we talk about the applications in energy, like water electrolysis and fuel cells, or as MRAM stack coatings for the application in digital storage devices. And finally, so different metal recovery techniques will allow us to recover and reuse this nickel either for the same process or for some other applications. So as you can imagine, NIC-EFFECT is quite a complex project with different tasks. So in fact, we could group these tasks in 6 technical work packages. We have 2 more. One is focused on the dissemination, exploitation, and standardization activities, and another one on the management. But here, in these 6 technical work packages, you can also see how different partners are interacting with each other. So in the work package 1, all the partners contributed to the development of the project specification. So that was an important step in the project to define clearly where we want to be at the end of the project, which kind of characteristics we are looking for, and how we will validate these materials characteristics at different scales. So then this document constituted the base for the work package 3, where we actually started to work on the development of these materials and assisting the process with the process modeling. We also have a part here inside the work package 3 that is more focused on the laboratory scale characterization. And this task allow us to make like the first preselection of the most promising candidate materials that later will be upscaled in the work package 5 and deposited on the demonstrators. So then finally, these demonstrators will be transferred to the work package 6, where they will be validated at relevant environments at the premises of the dedicated companies. So you can also see that there is a work package 2 that embraces all the other technical work packages. It is focused on the sustainable by design approach and incorporates various tasks like risk assessment, LCA, recycling, building of the decision support tool, data management system, and so on. It's quite a complex work package that has as an ultimate goal to enable good decision making and assist the material selection procedure that we will follow in the NIC-EFFECT. So this is the mechanism of this material selection. So if we focus our attention on this triangle, so we start from a pool of candidate materials that are based on nickel. And then during the project, we will be narrowing down the number of these materials up to the 3, the most promising ones that will be tested in real conditions. However, the material selection procedure is not based only on the efficiency of the deposits, but also is assisted by the modular decision support tool that incorporates the SSBD approach. Like you can see here, the life cycle assessment, chemical risk assessment, and environmental impact assessment. And we also incorporated here the materials modeling part that I will explain in a second. So once again, the main objective of this decision support tool is to basically build like an extensive database that will incorporate different sources of information, like for example the reference data, the experimental data, the LCA model, materials modeling model, and will allow the user to find more sustainable and safe materials based on the preselected criteria. So materials modeling plays a quite important role in the decision support tool that we are trying to build and integrate. And its objective here is twofold. First, it accelerates the material selection procedure by predicting the properties of materials even without the need to rely on the experimental data. And this is specifically important for us because we need to screen a lot of different compositions in a short time. And then once, based on the model predictions, we know we pre-selected the most interesting materials compositions. Materials modeling, again, can assist trial and error making in materials design by guiding the experimental work towards achieving the compositions with the preferable chemical and microstructural performance. So we also perform a chemical risk assessment inside this modular decision support tool that aims, as the title suggests, to analyze all the risks and hazards that are involved in the process fabrication of these materials that are of interest in NIC-EFFECT. So to do this assessment, we follow PDCA cycle. So we start from a method elaboration. We take as the basis some safety tools that have been already developed, but then we adjust them to the specific needs of the project. As the second step, the assessment is performed for all the partners through detailed CRA questionnaires. So then these questionnaires are analyzed in order to prepare some guidelines for the partners, but also the idea is that later these guidelines can be extended to other industries. And finally, the guidelines are incorporated in the decision support tool, so that will allow the user to pre-select the materials also based on these characteristics. So we also perform the environmental and cost impact assessment in NIC-EFFECT. So here you can see the 4 main steps of the LCA framework, but it would also work for the cost impact assessment. In fact, these 2 processes will be done in parallel. So the first step, we define the goal and the scope of the assessment. So we define the boundary conditions, the objectives, and so on for each of the 3 use cases. And we specifically take into account or consider the whole process, starting from the raw material acquisition and until the end of the life of the product. So then, similarly to the previous case, the data are collected through the dedicated questionnaires that are then assessed in the step 3. So this is where all the costs and impacts are calculated. And finally, at the step 4, the findings from the inventory analysis and the impact assessment are combined and the conclusions are drawn so that we can evaluate the sustainability of these materials and also to identify some hotspots that may require our specific attention. Okay, another thing that I would like to mention here is the process modeling that doesn't really support the modular decision support tool, but it assists the upscaling process of the materials that we'll be developing in NIC-EFFECT. So here the idea is to develop some realistic models by combining several models that are already existing, but also can be extended even further, taking into account the specific geometries of the materials that we target to produce. So this will allow us to achieve fine control over the morphology and the thickness of the coatings at different time and length scales, and also to perform some computer-aided engineering of the pilot cell. So for example, on this image, you can see a pilot line that we have installed at CDTech, and this is where we plan to prepare our demonstrators. So finally, at the end of my presentation, I would like to share with you this photo to give the presentation a little bit the human touch. These are the NIC-EFFECT people. This photo was taken at our first kickoff meeting in San Sebastian. So I'd like to thank all the consortium for making this project functioning. And of course, thank the organizers for giving us this opportunity to participate in this partner event. And also thanks the audience for your kind attention.
Thank you very much for this presentation, Leona. It was a really pleasure to have you here. Please save all your questions for the end and the Q&A session. And now I would like to give the floor to our next presenter, Dr. Maria Jacobs from Vito, who is the coordinator of the Nubeao project, the fourth project that is funded by the European Commission under the same topic. Dr. Maria, you have the floor.
Yes, thank you, Maria. Just share my presentation. So good morning, everyone. I am Marike Jacobs from Vito. Vito is a Flemish research institute in Belgium, and I'm the coordinator of the NUVO project, and NUVO is the Novel Electrode Coatings and Interconnect for Sustainable and Reusable Solid Oxide Electrolyzer Cells. So it's also one of the 4 sister projects funded on the same call, like FreeMe, Mozart, and NIC-EFFECT. So we are also a project focusing on safe and sustainability by design. And I would like to introduce you more about this project and what are the main objectives and the work plan of our projects. So first, let me say that NIVO is a 3-year project. We just started in September last year, and we are focusing on the application of solid oxide electrolyzer cells. And we would like to make them more sustainable and reusable by focusing on novel type of electrode coatings and also interconnect, which make it more complete, the whole cell. We are a project based on several parties, so we have different research organizations like CNRS in France, Forschungszentrum Jülich in Germany, the IMEO, the IMDEA Energy Institute in Spain, and also Vito in Belgium. Then we have a University of Technology in Eindhoven in the Netherlands. We have some small companies, QSR Lab in Poland, Marine Technologies in France, and VXL in Switzerland. We have also a big industry coating partner, Cotema in Germany. And we also have extended our partners with 2 associate partners, Acerinox in Spain, a metal company, and also VDM Metals in Germany as well. And if you would like to find more about NUVO, and if you want to follow our project, you can check our website, or also on LinkedIn, you can follow us. So why do we have this project? We are focusing on the solid oxide electrolyzer cells, and it's actually the most viable route for the efficient utilization of renewable electricity to produce, for example, green hydrogen or CO or other fuels. Compared to PEM cells or alkaline cells, as you can see here on this graph, by having higher voltages, the efficiency decreases, and by having higher current densities, you have a lower capital cost. And research is more and more focusing on having a high current density at a low cell voltage, So solid oxide cells are a promising technology for this one. And another benefit is actually that solid oxide cells don't make use of expensive materials like platina electrodes, like for example, polymer electrolyte membrane cells that uses platina. And here you see how a solid oxide cells look like and how it works. So we have three main components. We have a fuel electrode, electrolyte layer, and an oxygen electrode layer. The electrolyte layer is dense, but can also be a thin one, depends on which layer is a supporting layer. And we have the two porous electrodes. And by sending in the steam, it is converted to hydrogen, and the oxygen can transport through the electrolyte, and you have air at the other side. And you have to send in, of course, some renewable electricity to have this system operating at a high temperature of about 800 degrees C. Nevertheless, solid oxide cells don't use platina, but they contain some other rare elements like yttria, lanthanum, all these things. And with the demand for these earths expect to rise, and also the European Union heavily depend on this, on the import of these elements. It's not good if you want to scale up all this application in a long-term basis. So we would like to develop alternative materials for use in solid oxide cells, and also we will focusing on the recycling of rare elements for these cells. And besides the solid oxide materials for these three components, the electrodes and electrolyte, actually the largest part of the solid oxide cell is the interconnect. It's a metal interconnect, and it has a huge effect on the cost of these cells. And not only the cost, they also suffer from degradation as the chromium evaporates and things like that, and it degrades in the end our stack. And you would like to avoid, of course, degradation. You would like to have your cells having a long lifetime, and therefore to overcome these problems, we will also work on a lower cost metal interconnect with a protective coating to have cells that have a longer lifetime and a reduced cost. So here you can see the summary of our project scope and objectives. We will focus on the interconnect. We will have a reduced amount of chromium, and also on the electrolyte. We will focus on the recycling of yttria, and we will focus on a anode material where we'll focus on the reduction of the amount of rare elements. We would like to focus on lanthanum-free materials. And this we will try to achieve by employing innovative coating methodologies and modeling in combination with sustainable by design aspects and recycling options. And we aim also to reach JRL5 in the end. So some key numbers, we would like to go for 20% reduction of chromium for the interconnect, a recycling target of 50 to 70% of yttria, and also a reduction for at least 30% reduction of reduced amount of rare elements. And we will focus always on the composition, the coating methods, and also the upscaling in case of the anode material. So here you can see our work package distribution. We have the standard work package like management and coordination and dissemination, communication and exploitation. And then we have our two main material work packages like the sustainable oxygen electrode and the interconnect coating and integration together under the umbrella of the metal coating system for safe and sustainable solid oxide cells. Then we have also our work package on the eco-design, circularity concept, recovery and reuse. And this is all supported by the work package 2 by modeling, to also the modeling focusing on safe and sustainable by design. So first, let me say more about Nouveau's methodology and more specific on the materials modeling, machine learning, and artificial intelligence. There we will focusing on the developing of new material models and predictive models to develop and implement multi-scale bottom-up methods. So we would like to develop to do some virtual screening and to make some predictive models. And these predictive models can then be used to assist the material selections in work package 3 and 4 to have less need for all the experiments that you can assist the experimental selection of materials. And also here, it will be integrated with safety by design tools to support the experimental part. In work pack 3, there will focus on the materials development, so the use of no lanthanum and other rare elements. And we will use the benchmark coating technique like screen printing. This is led by CNRS. Then we have the materials manufacturing that are selected based on experimental work and the modeling of work package 2. This material will be manufactured by Marine Technologies. And then we have on lab scale spray coating of electrode materials, where there is an optimization of the microstructure by tuning the electrode material. And in the upscaling phase, we have the green ink development by VXL, and this ink will then serve for the slot high coating by Cotema to have a more faster and more efficient coating process to achieve efficient solid oxide cells in the end. In work package 4, it is focused on interconnect coatings and system integration. For the interconnect, there we have, this is led by Forschungszentrum Jülich with the support of Acerinox and VDM metals, and they will focus on new material selection with the reduction of chromium amount. This material will be used for the manufacturing of the interconnect, and they will apply a protective coating on it by different coating methodologies. And then the new interconnect will be tested, like, for example, oxidation test, composition characterization after this test, also the modeling of this testing. And you can see here an example of such a test where the weight gain is followed in function of the time during oxidation. And besides, okay, you have on the end the nouveau anode material, the new interconnect, and then all these parts should be brought together for system integration and testing. This will be done by VXL in Switzerland, so they have the knowledge to make a small stack and test this stack in the end to see the effect of the new coating systems and the new materials on the performance of the stack. Besides the experimental work, there's also a main work package on the eco-design and circularity concepts, focusing actually on the sustainability. So we have on one hand the life cycle assessment and design for sustainability, led by IMDEA Energy Institute in Spain. They will not only perform the life cycle assessment, but also focusing on the social assessment and the cost and the eco-efficiency to have the safe and sustainable by design approaches included there to support also the experimental part as well. We have also a part on recovery and reuse led by CNRS. They will focus on the recovery and recycling of the yttria from the developed cells. And in the end, the goal is also then try to reuse this material to make new solid oxide cells. We have also the toxicity studies. We're focusing on the safety assessment of the human exposure actually, and they will also in line with REACH compliance, and they will also use the SSBD strategy. And this is also done by FITO to study actually the health aspects of the new materials. So in the end, we would like to achieve a good impact with the Nouveau project. We would like to focus especially on the societal impact. Of course, solid oxide cells, they don't use the expensive platina or so like the PEM cells, so they score already better compared to PEMs. But of course, as they still make use of these rare elements materials, and the dependency of these rare elements and the energy demand will be significantly reduced if we can focusing on the recycling of the yttrium, and also if we can reduce the amount of lanthanum in our cells. So that will have a good impact on the environment as well. And if we switch also to the green inks for the electrode applications, we will have a more eco-friendly processing of solid oxide cells compared to the current solvent-based systems. So we would like to increase the circularity and the lower climate impact with Nouveau, and also the criticality of solid oxide cells by by focusing on efficient use of materials and waste management as well by recycling our materials. And with this, I would like to conclude my presentation with presenting you the people behind Nouveau. You can see here a picture of our team, of our project team at the kickoff meeting in Brussels at the beginning of this year. And I would like to thank FreeMe project for organizing this event. And I would like to thank you for your attention and for listening. Thank you.
Thank you very much for this presentation, Maria. It was really interesting to meet this project as well, and we expect that we will have more collaboration activities in the future with all the cluster projects as well. Now I would like to move on to our last presenter for today's event, Mr. Herman Altenrith, if I pronounce it correctly, from
Yes,
Robert Bosch.
yes.
It's an honor to have you here among us, and I would like to give you the floor to share your presentation.
Yeah, thank you very much for the kind introduction and the opportunity also to show here today concerning the topic digital twins in metal manufacturing. So I hope you can see my slides.
Yes, perfectly.
Okay, thank you. Yeah, so the topic here is a bit how can also the digital representation of manufacturing processes perhaps also support then the green transition. So it's from a bit another point of view, perhaps also some kind of teaser how this may influencing the plating aspects also. And I'd like to show you from a present use cases we have some insights of what we are looking for, and I choose one simulation or modeling technique where I think this could also be then perhaps relevant or is already in use, and perhaps some ideas maybe within it to understand. So it's from a thermal process, from nitriding process, and beneath that I want to give some kind of motivation and to perhaps show what can be understood under digital twin. So when we look for metal manufacturing, we have a process chain where several processes occur after each other with different sequences. One of these sequences for sure is then also the plating and improving the wear resistance of materials, but there are some processes in many cases before which may have influence on this process, and then some other processes which are then following these aspects. Yeah, and all these processes then influence our final properties of the component, and at the end we have complete systems. Complex systems where you have, for example, gears or some other bearings and so on, which have then to fulfill finally the requirements, and for sure which also should fulfill finally some environmental requirements also. The idea now is to you have on the one hand side this hardware workflow where the component is manufactured, and now it's also possible by acquiring data and by modeling to also build up some kind of digital representative of these parts, and then follow this manufacturing chain with the opportunities then finally to be perhaps better concerning the prediction of your quality measures or to improve costs during this processing chain. So can you hear me? So I have today, unfortunately, I have some connection problems.
Yes, now we can hear you.
Connected again. Yeah. So when we now come to this digital twin definition, it starts perhaps with some kind of product sheet where some information is given, but this is not really a deep information about an individual part. So let's say this is some kind of a low-level information for a component, but then you can go deeper in this field. And then you can, for example, get also data from the field itself. So what kind of loading did the part see? And when you couple this to the component, it has already much more value in it. And then the final part where I want to give my focus today is when you really look for the manufacturing and quality. So when you get information by each part or a batch of parts, how were these parts processed and what are the real properties of these parts. So when we look now for a processing, you have on the one hand side the process data, you have a process itself, and you have some kind of quality measure of the component. So this is now here a phase, a microstructure which is transformed to increase also wear resistance. But you can also say, okay, this may be then your plating process, which then increases this surface area hardness, and by this then the tribological benefits. And now you have here different methodologies you can apply. And one important, in my opinion, is the ontology, so the description of the process, that it can communicate with other agents, with other methodologies. Let's say it like this. So this is some kind of vocabulary for the process. And then you have here different methodologies, what you can do with the data. You can do data mining, statistics. You can also introduce physical models and so on. And the final goal is then that, yeah, you get some kind in benefit. So you have some money you can, yeah, you don't have to pay, or you have some time shifts, or you have the opportunity to get a more environmental friendly process chain. So this is the idea behind. When we look now for this ontologies, so what it is about. So you have on the one hand side here on the left side, you have the furnaces. So this is really the processing chamber itself. And there you have already quite different setups of these chambers. So it's now for a nitriding process, but though it's always a nitriding process, you have already differences in the kind of machine you have. And by this nitriding process, for example, you change here the nitrogen content at the surface, and by this you change then the hardness in this outer layer, and by this you can influence the wear resistance. And for some application, this is enough, but there are other demands, requirements where this is not fulfilled. But it shall show in tendency you have the furnace, and then you have your kind of results at the component with the microstructure. And now the challenge is that when you want to digitalize this aspect, you have in many cases very different formats of data. So you have Excel, CSVs, you have JSON, PDF, and so on. And when you now want to really evaluate the results, or you want to train models based on it, yeah, it's difficult to bring all this data together. And so now the question is, okay, how can we do this? And one aspect is now to bring this in a general format, and you can use ontologies for this. So, and now I want to show what are the steps you have to do to come to it, and show it with the example of this nitriding process, which may also help you perhaps to transfer this perhaps to your kind of processings. So you have on the left-hand side now, for example, a CSV file shown on the left-hand side. There are several parameters and so on, temperature, time, and so on. And now the first step, what we used was now first to transform this into a a JSON format, a native JSON. This means you have a bit more structured now the data in it. So you separate time series, for example, from scalar values. So this you have a bit in the format itself, but the JSON format, there's exactly the same content in it. So it's only the same, it's the same content, but the format, how it's used is now different. It's a bit more appropriate to the data which you have. And then on the second one, now you make a transfer from this original CSV files into some kind of a common language. So when you have, for example, a temperature, in Germany it may named Temperatur, in English it's temperature, and so on. And now you want that the program is now described in one language, and then you transfer this into this one language, which everybody can understand. Let's say it like this, or algorithms can understand. And so this is the first step. The next step you do, so you transform this into this canonical JSON, and there's some kind of vocabulary is behind. So, and then now you have now this this description, and to bring more information into the data, you couple the data points what fits together. So for example, when you have a furnace, the furnace has different different sensors. So it can measure the temperature, it can measure the nitrogen, and so on. And then you can couple that a furnace has some specific sensors. So you make always some triples. So sometimes some kind of a sentence to bring together what is part of each other. And so you transform this format here into a let's say some kind of more language which couples together the relevant information. And here is now shown a bit how it's set up. So you say, okay, I have a heat treatment process, for example. This heat treatment process has some objects, and in this objects, for example, is stored which kind of batch it is. But the heat treatment process has also some heating process, where then again some quantitative value within are stored. And so thereby you can build up this kind of tree structure. And by using these verbs here, or this connection paths, you can give the data, the information with what fits to each other. And that's a bit the idea behind the ontology. And so somebody which is now not focusing on the night writing process itself, when he sees this kind of representation, he can much more have an idea. So what is a heat treatment process, how it is set up, compared with when you have some kind of this format you have on the left-hand side. So that's the idea behind. And this you can also then apply for different kind of furnaces. So then, and the idea behind this, okay, now you have these different furnaces in your different plants and so on, but you can then use methodologies, so machine learning methods, which can then, based on this vocabulary, work with the data. And so you can scale up your methods, your statistical evaluations better. And yeah, this is the overview. So what are the steps you do? You have your data generation. This is happening during the processing. Then you transfer this into this vocabulary, where you say, okay, you want to describe your processes with this kind of vocabulary. Then you make these triples, so that you connect what is part of each other, what is a property of each other. So what dimension does a quantity has, and so on. So you get this tree-like structure. And then based on this representation, you can then use different analysis simulations and so on. But this is a first step you can do to bring your data in a better condition. Yeah, so I want to conclude now my my talk So I gave one example now for what is, in our opinion, an important aspect of the digital representation. You can use now, when you have this digital chain, you can use these methodologies quite good to find out optimization strategies. So it can either be time, it can be money, it can be sustainability, but you have to design this for your specific use case for sure. And yeah, I think the main points is, or the hypothesis is, that by using this digital data, you get new opportunities to optimize processes and thereby increase some efficiency. And yeah, I think for quite many projects, I think this digital representation becomes some kind of part of the project. Also new businesses can come out, and I think one aspect which can help is this ontology in a first step, to come from process component data to a more generalized formulation, where you then can build up on other techniques for optimization. Good. Then thank you for the chance to present here perhaps some other aspects, and if there are any questions and so on, I can kindly ask them. And I hope the connection was good all the time. So that's why.
Yes, it was. Thank you very much about this presentation. We are really thrilled to have you here today. So now I think we can move on to the Q&A session. Please write any questions you have in the chat box, or you can ask them directly. I think we already have one question, which was in the first presentation. So Alessio, I'm going to ask you to address this. It was about what about rack plating? Yes?
Maria, excuse me, just a moment, I'll get Alessio.
Okay.
Okay, just a moment, thank you.
Okay, so I think that, okay, I have a question about the Nugao project. So just a general one. If you could perhaps give us an intention of the scales where the materials are modeled and evaluated in the modeling base. Maybe we can start with this question, if it's possible.
Was the question for me?
Yes. May I repeat it, perhaps?
Yes, please, because I could not really get it, the question.
Okay, so could you please give us an intention of the scales where the materials are modeled and evaluated in the modeling base?
Concerning the scale for modeling, yes, we will. The modeling is not really a scale, I would say. Yeah, the general modeling, the basics modeling, the properties of the materials that are modeled, and also the aspect of safety are modeled for material selections. And then in the end, we will scale up the coatings and things like that. That will go up to TRL 5, but the modeling is more based on material level, not so much on a scale, I would say.
Okay.
That does answer your question?
Yes. Okay, thank you. Now, Alessio, are you back?
Yes, I'm here.
Okay, great.
Sorry. Yes.
So we had a question during your presentation about rack plating.
Rack plating, yes. So can you be more, I think, Mr. Buongiorno, right? Can you be more specific about the question?
Hello together. So question is, normally the present situation is that if you work with hexavalent and chromium, you have no rack plating.
Yes.
Because the hexavalent and chromium destroys the palladium colloid. So if you look into alternative solutions, for example, chromium 6-free processes like manganese, yeah, so you always face the problem with the rack plating. So now my question is, if you use your process with the spraying, how does it is with the rack plating?
Well, it depends. Of course, the peroxide route, for example, yes, one of the peroxide route for immersion is like the one with permanganese. Okay, so yes, of course, with all the immersion route that involve the peroxide rack plating, it is a problem that need to be assessed. It's something that the industry didn't yet solved. About the part regarding the painting, it depends if you integrate it inside a simple immersion, let's say as an immersion like tank where you do the painting. In that case, yes, you still have the rack plating, but the part with the spraying may require a separated section from the let's say from the plant, and in that case you can use a different kind of rack for plating and then for do the painting. In that case, you have solved in 2 steps. It's not quite optimal. I understand it right now, but it's not yet a problem that we are focused in. But in that way, you have just rack for the painting and the rack for the plating. And in that case, you can avoid the rack plating just because the rack you use for the plating is not activated, basically. So you will not have the plating on it. But yes, it's an issue that we have to assess in the future.
Okay, but this means then you have to jig twice.
Yes, exactly.
In different racks. Okay, I understand. Yeah, thank you. You answered my question.
You're welcome.
Okay, so I have another question. This is directed to Mr. Herman Alpenrich. So we saw about the digital twins. Do you think that the digital twins can be also applied in the plating industry? And how in general can the production process benefit from them?
So concerning the description, I think that the highest overlap is probably the processing itself, where also process data itself is available, or where quality data is evaluated. For example, when you make sketches and look how does perhaps the surface layer look like, or when you make some kind of quality testing concerning the wear resistance, for example. So I think these are the main 2 sources which come from. So on the one hand side, the information processing, on the other hand side, the quality evaluation, and then perhaps as another input also, what kind of materials are paired, what is coming in, and then and around this, beneath the experimental investigation, I think it's quite a good point to say, okay, when we now bring this data, which is evaluated then into a database, for example, and describe the data, that you can also use then methodologies to look how are process parameters influencing, for example, the properties itself. So I think this is always a very relevant question, and this you can make quite good on data. Or how strong is the scatter, for example, when we use this processing and you make 10 parts with the same properties, a campaign, how strong is our quality finally scattering? And I think for this, I think it's quite a good point to go in this direction. I could think that it's quite good transferable. We did not make it for this kind of process and quality evaluation. So we make it more for this heat treatment quality assurance. But I could think that perhaps it can also fit for the plating. But one has to look a bit perhaps more in detail and discuss. Yes.
Okay, thank you. We also have another question for you. Can the digital twin be also considered for real-time process of optimization?
So we in our company don't do it, but in tendency it's possible for sure. So, but then you also need some kind of feedback loop directly into the process. This makes it some bit more more difficult. So then it's more some kind of process, direct interaction, and therefore you need also models. So we don't make it. We are focusing more. Okay, you manufacture, the part is finished, then you make the quality. So you have longer loops. So in the other case, you really need very fast evaluation techniques, and you also need a data pipeline which is fast enough that you can really react within the process. And this is normally directly in the steering unit, and this is not that much our focus, but we know from companies that they are also doing it, and it can also be some part of this digital twin, perhaps in another interpretation.
Okay, Costa, do you think is this okay regarding your question?
Yes, sure. Thank you. That's fine.
Okay, thanks.
Thank you very much.
Now I have another question for Kostas. Do you think that the digital twins could be somehow be connected with the decision support tool?
It's from you, right?
Can you hear me?
Yeah, can you hear me?
Yes, I can hear you.
Okay. Yeah.
So can I
my
repeat
point of
my
view,
question?
Yeah. No. I understand. If I understand well, the question was if we can connect decision support tools with digital twins. Okay. So the answer is definitely yes. From my point of view, since from one side we have a digital twin that it can predict some outputs based on specific inputs. So you have from one side the simulation part of a process, and you can use this kind of simulation or regression model, or however it's made or model the digital twin. You can include this model into a more big decision support tool that is going to address even this specific part or even a bigger part of the process. So from one side, I could say to answer it in a more appropriate way, that a digital twin, from my point of view, could be one of the components of a maybe bigger decision support tool that we can have. But on the other side, you can also maybe model your digital twin as a specific decision support tool, and you can play with different scales. It depends on what are the boundaries of preparing your decision support tool, and the answer is yes. I don't know if the answer is it's okay.
Okay, yes, thank you. On this topic, if we stay in the decision support tools, I would like to ask another question. This is for the Nick Effect project. So, Aliona, this question is for you. If the decision support tool that is developed within your project is considering only the materials that are examined in the project and they have the experimental analysis to back them up, or if there is a freedom to have additional materials examined.
Yeah, thank you for the question. So we are trying to build this decision support tool using the Granta MI database. So this database already includes a lot of information regarding different materials and properties. So we will first create, let's say, our decision support within the Nick Effect project, but then when all the results will be available to public, we can extend it further so that everyone who has access to this database can use our data to find alternative materials, and also for us. So for us, we will be also relying on the data from the other scientists.
Okay, thank you very
Thank you.
much. If we don't have any other questions from anyone, maybe we can close this event by, actually, I have just a general observation that from all the presentations that we had today, I think that the plating industry is mainly driven now by the digital skills. So this is my main outcome from this event. I would like to personally thank everyone for participating today, and especially thank the presenters for their for sharing their experience.